I welcome everybody to the webinar on acoustic monitoring of suspended solids and natural engineered systems. And I'm really happy to have a really cool lineup of speakers of particle experts and sensor manufacturers and people who have used the technology in actual monitoring campaigns and projects even. And I'm also happy to got the endorsement of the IWA, the International Water Association, and the Association of Hydraulic Research. And why are we giving this webinar? We are running this in the scope of the CoUDlabs project, which is a collaborative project to build urban drainage laboratory communities. And basically, the idea behind this project is that we're building a community in urban drainage. And one of the instruments is that you can come and use our research and infrastructures. So we are not only doing research, we are also having networking activities and organize a couple of events. So the webinar we are organizing is part of the series of training. And if you visit our homepage on CoUDlabs.eu, you will see that we will have another webinar coming up on routine assessment of uncertainty. And at the Novatech conference, we will be having a workshop on the transnational axis where you can share ideas, what you can do with our infrastructures. And today we would like to give the webinar and discuss acoustic monitoring of suspended solids in natural engineered systems. And we have a lineup which goes from the characterization of particles and the problem setting, to the theory and the scattering, scientific instruments. And then in the afternoon, we go to the applications in urban and wastewater systems. So you see, we have two blocks of presentations, basically, followed with a discussion and with a coffee break. And the reason that we have a joint discussion is to maybe group discussion points, but also because we are recording the webinar. And we would like to make the individual contributions public later, and that is much easier for data privacy reasons. So without much further ado, I would like to give the word to Peter Vanrolleghem from the University of Laval in Canada. Peter is a professor in water systems, and he's been doing so many things, but lately he's focusing on particles and the overlooked role in particles in pollution assessment. So I'm really happy that he is sharing his knowledge on the relevance of particles with us. Peter, please share your screen.
Thank you, Jörg. Thank you, first of all, for the invitation. Of course, we have a history because I was for quite some time at EAWAG during my sabbatical, and this is a topic of high interest for me. Let's see whether I can share my screen. There we go. I hope that's fine. Somebody can confirm you're okay. Okay. So I'm at Modelot in Université Laval in Quebec, and I'm happy to talk about my view on why particles are important and why it's important to monitor them continuously in urban drainage systems. If I click on this, that should go. Yeah. I want to remove this one. So I'm going to go back to when I was first confronted really in detail with total suspended solids in urban drainage systems. It was a paper produced by a colleague of mine in Brussels. I was at the time I was in Belgium, Michel Verbank, and I'll translate this for those that don't speak French, but this was a symposium of the Belgian branch of the IWA that dealt with wastewater treatment operations and the high flow variations. This is 1995, so I just finished my PhD on wastewater treatment, and I was looking up and downstream of the treatment plant to see what's coming in. And in there, they talked about the variability of TSS loads at the outlet of the collection system. I was not really into the details of sewer systems at the time, so I had to learn a lot. And what I learned is illustrated best with this little two graphs. The first one shows you the flow rate at Brussels. And you see the dry weather in the beginning, and it's about 500,000 population equivalents. And you see 3 rain events. This is 35 years ago that these data were collected, which is relevant, I think, for the discussion. So 35 years ago, Michel Verbank and his team measured flow. That was not a problem. 3 big rain events. And you see how big those rain events can be in Brussels, a lot of runoff and gets into the combined sewer system. The consequence, however, is for the water quality. So first, let's look at the conductivity, which is an indicator of the dissolved material. And you see in dashed line the conductivity, and goes down, of course. These are the three events that you see. So you have the first event that goes really deep in conductivity. Second event goes even deeper because it's higher in flow. And then it goes into the third event. What they installed were turbidity meters, and they were able to correlate this with suspended solids. And what you see is huge dynamics. And the interesting thing, of course, is for the first peak, we had a first rain event after dry period. We had what is called first flush, and that's debatable, etc. But this was measured. The second rain event, the sewer line was cleaned, and you don't have this impact, even though the rain event was much bigger. And the third event, you don't see it either. So turbidity was there and informed us about suspended solids. I've been working on suspended solids for quite some time, and only recently I realized that suspended solids are a vehicle that transport at least 50% of the organic matter in a sewage system, the treatment plant. Nitrogen and phosphorus are contained in it in large amounts. Pathogens are attached to it. Heavy metals, one of the other particles. Hydrophobic micropollutants like pHs, pesticides are on there as well. And this is just a graph I found about pharmaceutical products. The yellow ones are dissolved, but the blue ones are present on the solids. So huge amounts of micropollutants there as well. And finally, if you bring sand to facilities, your pumps and valves and equipment are really suffering. So that was, I think, some of the messages I started to bring about a few years ago, that, hey, we have to look at these particles, because if you want to look at dissolve, which is the easy part, and model them and monitor them, you're missing most of the pollution. And particles behave differently in the sewer system than dissolved substances. So we all have these nice pictures in mind where we see turbidity, we see it, it's a visual impact. You might have really big particles, and this is what can happen if you don't take care of your sand coming in. Your treatment plant is basically completely full of accumulated sand and destroys your functioning. I think we all know how TSS is measured. You have a bank of filtration system, you have to dry, you have to cool it down, you have to weigh it on the balance, and there's some manipulations to be done in the lab. It's in the lab, which means all this is based on sampling. You cannot have a TSS measurement in the field just like this. Luckily, there's a relationship between TSS and turbidity. I'll just give you one example of correlation between what TSS turbidity measurements that are calibrated relate to lab TSS measurements. So you have much more details. Some sensors are more reliable, have less outliers, etc. So these are all the things that you end up with when you install such equipment in a sewer system. This is a graph I made in 1993 in SlideWriter, and I still like it because it expresses quite nicely the different principles of turbidity meters. One is transmission. You measure the light that's getting through from light on the right measurement device. You have backscattering, so particles will backscatter light and you will measure it when it's coming back. You may have forward scattering, which you can measure, and you might have the 90-degree scattering, which is called nephelometry. So on 90 degrees you measure. So all these principles have been shown to exist and work well in different situations in water systems. This is a nephelometer. It's a Solitax. You see the light emitter and the receiver, and it's on 90 degrees, and you see that these systems are subject to quite some pollution. This is the treatment plant in Quebec, where we have alum, which is added to the drinking water that ends into the sewer system and then leads to this type of problems. And luckily, there's wipers that keep the lenses clean, reasonably clean. Let's look at some long-term data. This is data we collected in 2012 in Denmark. You see the rain, the flow rate at the treatment plant inlet is combined sewer system. You see where the rain events happen. And you see in blue at the bottom, the period which is pretty good in the beginning. We call that pretty good. At the end, it's pretty good. And you see that the dry weather conditions after New Year led to slowly increasing suspended solids concentrators were confirmed by the suspended solids measurements we did in samples. What you see here is the period in which we were on holidays. we didn't go every 3 days to clean the sensors, and it led to accumulation, drift, and complete going off of the sensor. So cleaning is something that you need still, and you want, of course, minimize it. We will come back to that later. This is what happened really in the system. This is the same sensor after New Year. What you see is this blood little hair, which has accumulated in between the wiper and the lenses. And every time it moved, you basically had disturbance of the system with the wiper that brought the hair in front of the lenses. That's real life. Still, we can work with turbidity sensors and quite reliably if we choose them well, we choose the right type, we install them in a good way at the right location in a good corner, we do them regular maintenance, and then they keep providing good data. And even in a situation like this, where you think this can't work, it works because you have a compressor that puts air on the sensor tip and it keeps the location where you measure pretty clean. We all love these TSS turbidity relationships, but we know they are wastewater dependent, they're time dependent in location, and they're basically particle optical property dependent. So we have to do it regularly, and people don't care too much about it because they're mainly interested in dynamics, in seeing when things are happening and not looking at the absolute TSS values. But if you want to really go for TSS values in an absolute sense, you must do the regular calibration. This is data from Quebec again. So what is the value of high frequency TSS data? Well, I showed you, you would never see this type of behavior if you had an average sample, a combined, a flow proportional sample, for instance, for one day, you would have the average, nothing to be mentioned. If you sample, you must be lucky to sample like every hour to see these peaks, so you would have way too much work in the lab. So measuring in high frequency is important. This is from Brussels. This is probably the thing you know more about Brussels. Let's go to Bordeaux to see what we can do with high frequency TSS data that are being modeled. So what we have here is a validation of a model that was used to describe the flow and TSS concentrations arriving at one of the parts of the Bordeaux sewage system. You see a big rain event from day 57 till day 61. So long time series where the flow at the treatment plant was maximized, so high flow all the time. And then we drop back to dry weather from day 62 on. And the model was not perfect because we didn't include the RDII that was coming from infiltration of this large amounts of rainwater coming down. Now look at the TSS model that we're able to calibrate with such a turbidity measurements in the system. And what you see is that it's able to pretty well describe the behavior of dilution of the TSS. And then in this big rain event, and the first flush was not too big in this system, and then we didn't model the RDII, so the dilution that you had with RDII is not modeled well. We go too quickly back to dry weather conditions. So these models work, and these models help us to understand, optimize facilities that are dealing with suspended solids, and therefore we can handle those more than 50% of pollution. It doesn't always work well, as you can see here. These are other modeling results that are not as good as we thought they could be, but progress is being made, of course. My take home is TSS carries over 50% of important pollution, organics, nutrients, pathogens, micropollutants, and inorganics. The dynamics are fast, and therefore high frequency monitoring and modeling is essential for urban pollution management. The relationship between turbidity and TSS exists and has been used a lot, but there's problems that are remaining with the installation of these sensors, maintenance of the sensors, and the stability of this relationship. So the perfect TSS sensor should, and you're going to have a nice presentation about what's possible. The application I'll limit to is for real-time monitoring of particles in urban drainage and wastewater systems. It should be easy to install, require virtually no maintenance. Oh, wouldn't that be wonderful if you had no maintenance to be done? If we have to do maintenance, we should be able to do it easily. Let's say 10 minutes a week. We should have fast measurements within seconds and with a high frequency of collection. Hopefully we can have it spatially resolved because there is no homogeneous existence of TSS in any water system. It's always settling or whatever happens to it. We want it to be remotely working with lower power consumption. We don't need to provide energy, and it should be easy to calibrate. Hopefully we can have factory hard-coded calibration. And we want to measure not only suspended solids, but we want to have more. We want to have particle size distribution. We want to have different classes of material. We want to, for some reason, you like the 63 micrometer in Europe. Okay, we measure TSS below 63 micrometers, and we want to measure critical particles. With that, I'm going to finish my little story by saying, like, you'll have a lot of information coming, learning about how TSS can be measured in a different way using the acoustic modeling methods. Thank you.
Yes, so my talk will be about acoustic scattering from particles. I will speak a little bit about theory and then show you some examples done with scientific instruments. I'm Stefan Fischer. I'm the founder of the Ubertone company, and I'm also in charge of research and development in this company. So just a few words about our company. We are a small team of doctors and engineers here in France, in Strasbourg. We are developing and manufacturing acoustic profilers, mainly for scientific research, but we also do some sensors for environmental monitoring. We provide sensors that, measuring velocities, velocity field, and backscattered echo. That we can also speak about turbidity, acoustic turbidity. We do this measurement accurately with a high resolution down to the millimeter with fast installation. We do measurements from the lab to the field. Of course, as it's acoustic measurements, we can measure in opaque liquids, and this is for a wide range of applications, typically from civil engineering up to chocolate manufacturing. So here we have a few examples of our instruments. And but now I will just switch from Peter's talk to acoustic turbidity. To acoustic turbidity. And so from my opinion, one of the major limitations of optical turbidity for measuring the suspended sediment concentration is the sensitivity to the size of the particle. Actually, here you see this graph from a publication from Tolle that shows the relationship between the backscattered intensity of the optical turbidity meter to the suspended sediment concentration. And as we see, so for very fine materials, we get a high backscattering, and as we increase the size of the particles, we get less, for the same concentration, we get less intensity. So this is because there is a relationship between the wavelength and the particle size, as seen in this graph. For particles above 1 micron, for higher size, we get a lower signal, which is not the case in acoustics, as we will see later on. Because with acoustic waves, we can get wavelengths over 50 microns. So just a few words about acoustic waves. Acoustic waves is defined by a frequency. Okay, we emit a frequency in the medium. These waves travel by compression of the medium. So this frequency define what we call the ultrasound. Okay, it's the sound above what we can hear, so above the audible sounds. And this acoustic waves has a wavelength. Okay, this wavelength can be defined as this formula as a ratio between the sound speed and the emitting frequency. And by changing the wavelengths, we can change how we are sensitive to a given particle size, and we will see this later on. So now just a basic about acoustic beams. What is an acoustic beam? So we use a transducer for emission and reception of a signal. This transducer, basically, it's a piezoelectric ceramics that is compressed by electric waves. And once we enter the medium, the density of the acoustic waves will travel as this complicated form, okay, that we can numerically compute with this formula. But basically, from one transducer, we have first near field in which almost the beam can be considered as a cylinder, and then we have a cone that diverge in the medium. And so we bring energy in the medium within this beam, and we get back energy from the scattering of the particles in this beam and only in this beam. Okay, the near field can be defined as here, but if you're more interested in such details, you can have a look to our YouTube explanation about the acoustic beam and the details on that acoustic beam. So now about acoustic scattering. As we emit energy in the medium, this wave will travel inside the beam and will catch several particles in suspension in the liquid. And each particle will get a small piece of this energy and send it in all the direction almost, okay? And as it sends energy in all directions, we can get a small part of this energy back to the transducer that works in emission and then in reception. But as we increase the number of particles, we also increase the energy we get back. And if the large particles are larger, we get the same, okay, increasing of the backscatter. Now, as we send a pulse, we can listen to the wave that comes back from the medium at different time after emitting the pulse, and from the traveling of the wave, and because of the sound speed, which is quite low considered to the optical wave, we can get information at different distance. Okay, here we have an example of the backscattered echo that comes from a river, and we get backscatter echo as a function of the distance. Acoustic backscattering can be easily defined by the sonar equation. Sonar equations that gives the voltage on the transducer as a function of the concentration, with a part that comes from the scattering of the particles and constant from the transducers and from the system, and then attenuation. So here the exponential, the decrease exponential refer to the attenuation. Here, this Ks, which is the backscattering from the particles, can be described as this formula. Here we have the form function, which defines the sensitivity for given particle size to a given wavelength. We will see this after. And on the other side, we can express the attenuation with this formula that gives the attenuation of the water added to the attenuation due to the scattering of the signal, to which you can add the vicious attenuation. I will not go into the details of that now. But this form function is very important, as we will see later on. We can also define the acoustic turbidity, which is it's quite a simple expression of the energy we get back from the medium divided by the energy we send in the medium. And this acoustic turbidity, which is calculated from the voltage we get from the medium, is a good representative of the scattering of the particles in the medium, and is independent from the instrument. So this is some processing from the voltage that you can get. Now, back to the form function we had in this formula. Okay, so the voltage is dependent from this form function, and this form function can be expressed like this. It's for here we have the value of the form function as a function of Ka. So K is a wave number, and A is the radius of the particle. So if we increase the radius of the particles, we get a high value of the form function and then high value of the voltage on the transducer. On the other side, if we decrease the particle size, if it's sufficiently low considered to the wavelengths, we get nothing from the medium. But this is for sand, and we can get also similar model for silt, for flux, for any kind of suspension, but each suspension has a specific form function. This second function is the equivalent of this form function for the attenuation. Now, if we put this form function back to the sonar equation, what we get is this function which represents the backscattered intensity for a given emitting frequency. Here we have the 1 megahertz emitting frequency. We have the same properties for optical backscattering, but in the case of optical backscattering, this function is shifted at a very low value of the particle size. This is why we have this decreasing as we have it on the acoustics. We have this decreasing of the sensitivity as a function of the particle diameters. But now, as we have this function for one emitting frequency, we can use different emitting frequency in order to shift this sensitivity function in order to scan a wide range of particle size. So ideally, by having particles from the micron to the millimeter, we would need frequency from the gigahertz to the megahertz. So unfortunately, for acoustics, it's not possible to reach the gigahertz value, but at least we can work from the megahertz to a few tenths megahertz. Having said this, it's important, as we see, to have the possibility of having different emitting frequencies in order to have the access to the different particle sizes. Also, the bandwidth of the transducers allows a better frequency scanning. So this is why having a wideband transducer is quite important. Also, due to the fact of the huge variation of the echo intensity as a function of the distance, it's also important to have accurate amplification with a variable gain. Once you have this in your hand, so getting the backscattered signal from the medium at different frequencies, now it's time to invert this data to get the concentration and to get the particle size. For this, we have different inversion methods. One of the most known is the dual frequency, but I will let this explanation to Céline Berni in the next talk. She will give you more details on this inversion method. Now I will switch to a few examples from this theoretical basis. So here we have an example of backscattering in an aeration tank in a wastewater treatment plant with a quite important concentration of sediments. And as it's an homogeneous medium, what we get as a turbidity ratio is a very simple expression of a decreasing exponential. On these two parts, we have first the backscattering, which is proportional to the concentration, as well as the attenuation, which is also proportional to the concentration. So if we look our turbidity ratio as a function in a logarithmic scale as a function of the distance, we just get a line. And from this line, we can easily get the concentration once the system is calibrated for this given suspension. Here is another very simple example. And as we see, we have a nice linear relationship between the concentration and the backscattering, as we have with optical turbidity meter. But the advantage here is that we can use different emitting frequency to get different function of this relationship between backscattering and concentration, and then get back to not only the concentration, but also the particle size. Here another example of backscattered echo in wastewater treatment plant, so in wastewater. Here we are in a clarifier tank with a sludge level at about 1 meter depth. So the system is looking down, and what we detect easily is the first step here, which is the sludge level, and then we have an attenuation from the sludge itself. The interesting point here is that the attenuation here in the water with suspended sediment and the attenuation here in the sludge is quite different, and this is due to the density of the materials. Here another example of suspended sediment concentration. Now it's in a sewer where we could follow the concentration during the time and compare it to sampling. With still the same system, so the SEDIFlow, we follow the concentration of fine and coarse sediment in a river. So we distinguish the particle size above and below 63 microns. So we could move the system from one side to the other side of the river and follow the concentration changing in the time during the flushing event of the Rhone River. So, here an example where we can we see the interesting of adding velocities with the backscattered echo amplitude. We see here the velocity profile, and the interesting step here was quite surprising. But as we see on the backscattered echo, we see that we have an increase of the concentration near the bottom. Actually, this is the expression of a moving bed in the sewer. So sludge moving slowly at the bottom of the sewer. And the last example of a mix between measuring acoustic turbidity or backscattered echo with velocity fields. This is done with our UBLabs 3C. It's a prototype for measuring the suspended sediment concentration and three-component velocity vector in the field. Here we can follow during one wave the velocities on the beach, and so positive and negative velocities, followed by the concentration measurements, so the gradient of concentration above the sand. And at the end, we can calculate the flux of sediments, because the team at Brest was interested in getting the sediment transport on this beach, because sometimes during storm events, the sand is fully removed or sometimes fully back during these events. You can have more details here on this presentation. So as a conclusion, acoustic backscattering allows to monitor the suspended sediment concentration in sewers and in rivers. Using a wide frequency range allows to resolve the particle size distribution, and getting the echo profiles give access to the full field of the concentration. Thank you for your attention.
Thank you very much, Stefan. That was a fascinating presentation. It's also very good to see that you have like already a range of applications under your belt. And as you said, like now we would give the word to Céline, who will report a bit more on the inversion and making sense of the monitoring signals. And maybe you can share the screen. Céline Berni is a researcher at INRAE in France. INRAE is a public research institute working for the coherent and sustainable development of agriculture and the environment. And Céline herself is a specialist on sediment transport and is working on the sediment hydraulics, mainly with lab experiments, but also working on acoustic techniques.
Thanks a lot. I hope everybody sees my screen. So today I would like to talk about experimental evaluation of hydroacoustic models and inversion methods in rivers. So, there, my slide I should. Okay, it's okay. So this is mainly a PhD works of Adrien Vergne that I co-supervised with Jérôme Lecause, working also at INRAE. And you'll see that some developments are following right now with Brahim Moujed. So here we talk about rivers. In rivers, you also have sediments, like in other systems, and mainly those sediments can be categorized in two categories. So mainly the coarse one that are sand and that are more close to the bed, and the fines that are well spreaded all in the water column, and that are finer. Usually, so what we do is that we do some grain size distribution analysis, and then we can see that something that is quite often see in the rivers is that we have fines and sand, and so we have this bimodal distribution of sediment. I won't talk more about these slides. You saw all the impacts of the particles in the first presentation in urban drainage system, and it's the same actually in rivers, because we also have this pollutant that are attached to the sediment. We also have problems of sedimentation, flooding, and everything. And so that's why it can be quite important to quantify those suspended sediment fluxes, both fines and sand. So as you saw with the Stefan previous presentation, we know how to do acoustic inversion for sands. We did some laboratory experiment to calibrate and to determine the form function of those sediments, and we did develop inversion methods, and we were able then to compute concentration in time and space with the acoustic signal. But what about rivers? Can we use those ocean models for rivers, and especially all the form function that have been derived mainly for sand? So we tried this, and we went to the field with a boat, and we did the measurement of backscatter with an acoustically calibrated multi-frequency ABS. So this is not the same as Stefan showed you, but quite similar system actually. And we did also samples. We measured concentration and grain size distribution, and we applied those acoustic model. I won't go into the detail of all this equation. There's no need here. It's just to show you that then we are able to compute the signal that we should record, the backscatter signal that we should record from this acoustic device as a function of the depth. And then we were also able to measure it. And what we obtained was dramatically different. So now the question is why? Where does the problem come from? And from this, we had possible answers. First, the previous models that are mainly developed for sand does not apply to fine sediment. And the second option is that there are other scatters that exist within the river. And after this, we can wonder whether we can nevertheless measure suspended sediment concentration from backscatter, and when. So now we can go back, we can first have a look on acoustic backscatter of fine sediment. So we go back to this bimodal river sediment distribution. We know that it's okay for sand. We know how to deal with it from previous work. But yeah, going back to literature, we think that there's only a few studies that were dedicated to fine sediment backscatter, and we were interested in knowing more about it. So we did laboratory experiments with river fine sediments. So those lab experiments were handled in some small tank with pumps and agitators to put sediment into suspension, and then we did some acoustic measurements. So we measured the sediment attenuation that Stefan talks to you about, and the backscatter, so how well the particles reflect the signal. And we did also samples to compute concentration or to measure concentration and grain size distribution of the particles that were into this tank. Those were particles that we took from a river, actually. So with this concentration and this grain size distribution, applying the acoustic model for attenuation and backscatter, we were able to compute attenuation, this, and backscatter. So those in the vertical axis are what we model from existing models. And the measure is on the horizontal axis. And we see dramatic differences between what we measure and what is modeled again. So which confirms that the form function, all the acoustic models that are developed for sand does not necessarily apply to fine sediment. And that's exactly what Stefan said. We need to calibrate for each type of sediment. But then another question was, okay, but can we really measure well the particle size? And what is the particle size for such fine sediments? So we tried to shift a bit the grain size distribution that we obtained from measurements and tried different combination of grain size distribution to see whether there was one that allowed us to fit well what we measure. And indeed there is some distribution, the blue one here, which is not that different actually from the black one. And with this blue distribution of grain size distribution of sediment, we do have a good agreement between what we model and what we measure. So maybe we are able to apply previous model to fine sediment. So if we go back to rivers, acoustic backscatter in rivers is significantly different from what acoustic model predicts, and it can be partly due to fine sediment response. We have difficulties in applying spherical model and finding the representative diameter, and this is no surprise if you look at this picture of the fine sediment. All the sand or previous models for acoustics are basically based on the fact that the particles are more or less spherical, which is far from being the case for fine sediment. So finding a nice representative diameter of such a particle is not that easy. So if we adjust this diameter a bit, we can get concentration from acoustic signal, and that's what you can see in this publication here. If you want to know more a bit about this research work. So, okay, we do have differences in fine sediment response, and can it explain all? So we go back to the field. Here's Lyon, where I live. The Rhone River is in blue, and the red stars are where we did some measurements. Mainly we did samples and acoustic measurements. And then we computed the backscatter of really the near surface water. And we again compared what we measured near the surface from what we modeled. Now there's some change, sorry. So this is what we model for backscatter, and this is what we measure. And you see that for high frequencies, there is a good agreement between measure and model for the backscatter, but for low frequency, there's a dramatic difference between field and lab, and it's up to 100. So this is not in, like, the lab difference that we saw for fine sediment is not enough to understand what's happening in the field. So there should be other scatters. So first, we can see that the fact that the backscatter we measure here is increasing with concentration can say, okay, maybe this is something linked to sediment, even though this is not purely the fine sediment that are backscattering everything. Maybe it's something linked to the sediment, so it could be aggregates. It could also be turbulence. It could be also air microbubbles or microorganisms, and we don't have answers for everything, but we'll just have a look on air microbubbles. And just before that, you saw that the disagreement between measure and model depends actually on the frequency. So we can plot like the effective backscatter as a function of the frequency for different particles, fine particle, flux, sand, microbubbles, and you can see that all of them do not have the same behavior as a function of the frequency. In white, this is the zone where we measure with our system. And you can see that for bubbles, it's mainly flat. And for fine particles, it should increase at a constant rate. For flux, a bit different. And for sand, there might be some saturation for high frequencies. So let's see bubbles. So we saw that we have different behaviors of bubbles versus sediment as a function of the frequency. If we compute some x, such as the x that corresponds to this slope, actually. So it's such as the backscatter is proportional to frequency power x. We saw that for sediments, it's about 4. And we can compute it also over a cross-section of the river. So this is the depth of the river, and the flow is going perpendicular to the slide. And so we are going from the left side to the right side of the river. And we can somehow compute from the different frequencies signal, we can compute this x. And we see that in most of part, we have something around 3, 4. But in some part, we have something very close to 0, which is very close to the surface, actually. And yeah, we do think that it can be bubbles that are backscattering the signal, and that's why we have those this 0 slope for the behavior of the backscatter versus frequency. So again, if you want to know more, I suggest you to see those publications of INRAE. So, okay, go back to rivers. Okay, the difference in between rivers measurements and model can be due to fine sediment response or other scatters. But can we still use those acoustic devices to do sediment concentration measurements? And yes, it can work when everything is fine. And actually, that's what Stefan showed you. He showed you like very nice results about dam flushing. And it works when there's enough sand, so that the sand dominates scatter. It works when there is enough fines, so the fines dominates attenuation. And we can make it work under several assumptions where the fine grain size distribution is homogeneous, the sand grain size distribution is homogeneous, and both sand and fine concentration can vary within the section. So you have some image on the right where you can see that we have mostly fine sediment and not that much of sand. So you can imagine that this could be the grain size distribution near the surface. And if you go deeper, then you have more sand and less fines, and this could be the grain size distribution. So this is what we allow, a different proportion between sand and fines in the models that we use. So then what do we need? How we do the things? So we do acoustic backscatter measurements, and we do also near-bed samples with a large concentration of sand and all the samples above it. Then we do some backscatter model for the near-bed samples where sand dominates. And then we compute attenuation. And then we apply this bifrequency inversion method that Stefan talked to you about. Now, I won't say much more about it, actually, because I don't want to go into the detail of such a method, but with this we can estimate sound concentration everywhere in the section, and we can also compute attenuation in the section and then find concentration. And you can have the details here, but I won't go into it. But all this can be written in terms of equation also. And this is an example, field study, where we have the dime flushing of the Isère River and the Rhône River, and we did measurements here along this line at the confluence of the two rivers, acoustic and sediment and samples. And this is the acoustic results that we get from inversion, where you can see the Isère River that was very loaded with sediments, and you can see here the Rhône River with clear water, and the Isère that goes beneath the Rhône River with this turbidity current, let's say. So here are the results for fine sediment and sand. You can see that we cannot see all the cross section because we have blank zone where the acoustic is too attenuated. But for the rest of the section where we do have acoustic measurements, we see quite well agreement between the concentration that we measured with the samples and the concentration that we get from acoustic. So it seems that it's working, and again, it gives you a much nicer overview of what is happening within the river cross section that what those few samples can give it to you. So again, I put all the assumptions that we need to do for this method to work, but it might be not so easy to apply it. So that's why we are currently developing a software to help with the inversion. And I'm a bit late, so I guess I will let you read this, but there's only 4 main tabs: to see the raw signal, to process the signal, to process also the samples, and to get the inversion. And this should be available soon. And with this,
thank you, Jörg. Just a second. Visible?
Yes.
Okay, thank you very much. Yes. My name is Kibrom. I'm working at the NIVUS company in Germany, which is, let's say, a market leader, one of the market leaders in flow metering. And a specific technology that is related to us is the correlation sensor for flow measurement. And recently we have started R&D for a sensor called Pecher, which is a particle concentration measurement system. And I was mainly responsible for that work. So today I want to present the first insights we got in the last 2 years after market introduction. So the beginning, or the starting point was, of course, to in general to have to complete our product portfolio in terms of also measuring quality, meaning that we want to detect the concentration or the mass flow actually that exists in sewer networks, for example, as one application area. And in fact, we had in early times a few of those optical spectrometer probes. But what we have seen is that there is a high maintenance demand, and you have to use air pressure generator, for example, and in order to really blow off anything that blocks the optical path. And yeah, the reason is very simple. So very often, I mean, in general, those spectrometer probes work quite nicely, but in those application ranges or application areas we have, they are usually susceptible to drift, and this drift is very often caused by the blocking of the optical path. So the motivation was to go ahead and see whether we can have something more practical. Practical not only means that we want to do easier mounting and operating and maintaining, but we also want to achieve upscaling. That means that we want to have a technology that can be fabricated, tested, end-of-line calibrated in an efficient manner, so that once we are in a scale of hundreds or probably even thousands of sensors, we actually reach the industrial range. And if you go to that point, you really have to rethink a few aspects of particle measurement. So, of course, it is about continuous and time resolved measurement. And what we as a company have is that we have a very large experience in designing and fabricating ethics-related sensors. So we fulfill this requirement very often for a very large range of our product portfolio. And in fact, at the final stage, we also want to have something that can do combined measurements. That means flow and yes, in this case, it's a acronym for SSC, but of course, what is meant is TSS, total suspended solids, and to have this combination of parameters in order to really measure mass flux in the channel. The sensor itself looks quite similar to what you have seen from the presentation of Stefan Fischer. So in general, when you go into canal or into those application areas which we have as a company, you very often consider such kind of design of the sensor, because with such a design, you simply can avoid large, let's say, these blocking issues which you can get easily when you have a very improper sensor design or sensor casing in the flow. So this sensor is called PKM. It's a German word or German short form for particle Konzentrationsmessung, which simply means particle concentration measurement. And of course, on the other side, you need also a transmitter. And this transmitter can do various standard communication interfaces, Modbus, HART, whatever is used in those application areas. And this again is the type so-called NIVUS PAR-Q. And what are the specifications? Very short. So as I said, we have a frequency range from 1 to 9 megahertz and 6 grams per liter in max, what we can measure, and 5 size classes where we resolve the particle size distribution. And the beginning of all this work was an R&D project which we had in cooperation with the University of Stuttgart. And the first results with the, let's say, handmade sensor, as you can see in the picture below, is in fact has been applied into the inflow of a treatment plant in Stuttgart. So the first results showed us, okay, in general, this method works quite well. The techniques, the electronics and so on, the complete system works quite nicely. The concentration day cycles were quite nicely visible, as you can see it on the left picture. And the same we did also in rainwater applications. And there we had similar results, and we could see that in general, in a first step, the sensor concept worked quite well. So the major challenges we have observed is, of course, mounting and installation. This is actually where we have our big experience in. So we did flow meters in channels in sewer systems. So we know how to build sensors in a way, or how to mount sensors in a way that you can avoid blocking by large obstacles or sedimentation. So the sensor calibration is also very important, of course, as the experts before have told. And the other thing is also to find the best average material parameters, not really the specific to each component in the medium, but the average material parameters like mass density and so on. And you can achieve this by laboratory calibration. It's one way to do it, and the other way is to really do some kind of in situ calibration. So mounting and installation, this is what I have said, something that we have a very large experience on. And usually sensors are mounted in a way that they're put to the bottom of the channel or to the channel sole. And you can also shift it a bit sidewards in order to avoid sedimentation. But the accessories or the equipment, the mounting equipment we use is in fact one part of our product portfolio. It's very specific, where we have a large range of various accessories that can be used to mount those sensors. And one thing is you want to put those sensors into a channel, or you also have applications where you want to measure discharge or overflow. And therefore we have also, again, specific mounting options. But sensors can also be drilled directly into the wall of a overflow or discharge threshold. So again, a bit more detail about the sensor itself, just quickly. So the channel, or the sensor consists of various parts. One is, of course, the mounting plate, which is made of mild steel usually. All parts are usually made of high performance polymers, so that they are quite robust in such media. And in the front, at the front, we have the transducers, and at the back we have usually something that can protect again, against entanglement at the backside, for example. And we have already two sensor versions. One is for water levels that are starting at around 7 to 8 centimeters. Below that, simply due to blocking range of the property of the sound field, you cannot measure below that level. And the other sensor, this water level, this minimum water level that is required, is around 15 centimeters. So then there is the part where we have material parameter estimation or derivation, and therefore we use laboratory. That is where we can do some very good homogenization of the suspension. And we also did in the past something that is called BCAS protocol. Maybe you can look it up. There are quite some publications about that. And all this together is something that we have in-house in our headquarters. And that's one part of how we derive material parameters. The other part, of course, is how we then do end-of-line calibration. This is done usually in a way that is feasible for us as a company. So we need to consider staff training. We need to consider how to maintain, how to keep things in the proper state. So we have to use something that is very simple. And in this case, this is just a beaker with a steering, a magnetic steerer that can be used to do some simple homogenization of quartz particles. And we use that in order to derive the transducer efficiency and the transducer function. We have a separation between near field and far field. Stefan has already talked about it. And this is a very essential property of the sensor. Then, of course, you can do, once you know how to calibrate, how to derive parameters in the laboratory, you can do in situ calibration. So one way how you can achieve that is to just use a large sampling vessel where you have your original medium, using a pump, for example. You can resuspend this and see what is the result from the sensor and compare it to sampling. Or you can use automated sampling that will be shown from Frau Beckmann, Mrs. Beckmann from Pecher AG. And once you got all this, you can think about really doing measurements. So you have the property of or the characteristics of the transducers in your sensor. You have first ideas or good approximations of the material parameters, and then you can collect data on concentration, overall concentration of TSS. And as you see here, it really dissolves nicely on the dynamics that exist in the channel. For example, on the left, we see that the TSS inflow increases, the discharge increases with a little bit of a time shift, and this is around at an inflow of around 600 liters per second. The same or similar picture with an inflow of around 600 liters per second gives a much more different inflow in TSS and also in discharge. So The question here now that arises when you do this kind of measurements, which is just a simple example, you have to think about how to compare it to the data that you get from sampling, as I have described before. So questions that arise are, for example, related to the German guidelines, which are the A102, for example, which is describing the IFS 63, which is particles, TSS particles smaller 63 micrometers. And the observation currently for us is that the field data shows a major fraction that is much larger than 63 micrometers. So the question that arises is IFS 63 or TSS 63 is really strongly dependent on boundary conditions. So how can we compare that to the knowledge that has been derived from particle analytics? This is a very important part that is currently, let's say, ongoing work. But the other part, of course, is if you're able to really separate the particle fractions. You have on one side the zero networks and this kind of parameter that is defined below 63. But are you able to, in general, to really resolve over all fractions? And what we have observed is, for example, in hydropower, that we in fact can get very nice results in terms of all fractions that we detect. And one example here is at the inlet of the water intake. So the motivation for measuring there is, of course, avoiding hydroabrasive wear on exposed turbine components. And this was a nice project where we have, let's say, the first time also observed a very broad distribution of particle sizes over all classes that we detect. So in summary, the point here is, of course, first and for all, the major challenges that exist in zero networks. So I have talked about mounting and installation. This can be improved significantly by the proper design of the system. Calibration of sensors is I mean, the main point here is end of line. That must be feasible. So you are scaling up, so you want to go there to 100 or 1000 even of sensors a year, probably, if it's working good. So the program, you need to be pragmatic. You need to be simple and fast in calibration. So this is done by stable suspensions of quartz sand. And this is actually the reference material that we use for the material correction factors. About this point has been talked about in the previous presentations. So material parameters and correction factors, the most robust approach that we have seen or that we have experienced is this large sampling vessel concept. So calibrating within it in situ by resuspending. And the next steps that we want to go here is to even better understand how to compare sensors to samplings, as I have talked about in the previous slide. And the ongoing projects, R&D projects in zero networks, we want to use these projects in order to continuously develop the measurement method and further improve, of course, the calibration conditions. They are probably not perfect currently, homogeneity of suspension in calibration, of course, and also to include fine fractions. So that's basically, I hope, a good overview of what we did at NIVUS and what we experienced from the first projects that we did with the sensor. Thank you very much.
More or less.
Yes. Thank you, Jörg, for your introduction. Hi, everybody. I'm going to present you a work that is not connected so much with my current work in my postdoc. But is connected with this webinar. And I did this work in collaboration with the EAWAG in the past during my PhD studies. So as an introduction of this presentation, I will highlight some of the issues that the rest of the speakers already mentioned, like, for example, that in this study, we focus in analyzing the particulate matter, also referred as suspended sediment concentration, or TSS, as a typical proxy for Ubertone assessment. It's very important, this parameter in the last decades, to detect how pollutant is the system. And also, I would like to highlight something that was also mentioned in the last presentation, that nowadays the new directives, the new European, but also in every country, is increasing the challenges of measuring and monitoring in order to reduce and protect, reduce the pollution and protect the water bodies. So we must highlight this as well, that monitoring is getting a big presence in these systems. As a research gaps in this case, we were focusing in the limited knowledge of the dynamics of the particle matter in the urban stormwater and combined sewer systems, because as is already mentioned in this webinar, the particle size distribution plays a main role and can destroy these regressions, relationships between optical turbidity meters and the TSS concentrations. And so we just perform our research based on in order to try these acoustic backscattering profilers, in order to prove that they are sensitive to the suspended particle concentrations and also to the size classes. And for that, we performed 2 experimental campaigns. One was in the lab of the facilities of EAWAG, and the other was in the University of A Coruña in a flume test facility. And we were focusing the fine particles, those below 63 microns, as the German guidelines highlight, because these particles suffer or increase the absorption of pollutants. So the first experimental campaign was, as I mentioned, in the EAWAG facilities. We used this. I'm going to change the pointer. So we used this small channel with a length of almost 4 meters and 10 centimeters width. We have a closed loop with a retention tank. We use this the Ubertone sensors, the UV flow and the UV lab. In total, we installed 3 transducers of 3, 6, and 9 megahertz. We used 2 types of particles. One is the plastic material, the PMMA, these spheromers that has a density of 1.2, so very close to the water density, and was very easy to resuspend or keep the suspension of these particles. And we also use the milliseal sand. The concentration that we test range from K0 to 1,200 milligrams per liter, and the particle sizes were from 10 to 16 microns. We performed 2 setups, one just recirculating and keeping the suspension in the tank, and the second setup was introducing the pumping and the closed loop of the flume. In the first setup, we placed the sensors like the UV flow and the 2 transducers of the UV lab inside the tank. We have here the stirrer. We also have other sensors like an scan proof and other turbidity sensors, but I'm going to just focus on the acoustic measurements. And as I mentioned, in the closed loop, we installed the transducers and the sensors inside the channel, as you can see here in the picture. In order to get a good measurement for the transducers, in case of this UV labs transducer, we point it horizontally, so we have more beam to measure the concentrations. Just to summarize, in the first part of the webinar already present the equations. We use the exponential decay of the turbidity ratio profile, and it looks like this. So we can use this this equation, taking the two big considerations or two big assumptions. As first one is the uniform, that we are assuming uniform particle size and also density distributions along the transducer beam, and this is a huge assumption. For example, in seawater, because we know that sometimes it's not uniform the concentrations along in the vertical axis, for example. But in this case, we were like trying to keep, for example, with the plastic particles, an homogeneous suspension, so we can take this assumption into account. And basically, this is a relationship between the beam distance and the turbidity ratio profile, and I would like to highlight the parameters that we are changing. One is the concentration, also the sense class, and the emission frequencies. And if we just play a little bit with this equation, we can get to a linear equation in the logarithmic domain, and we can extract or to get two features from this from this equation, which is the slope and the intercept of this linear relationship. So basically, avoiding the first centimeters, as Stefan mentioned in his presentation, that they are quite unstable, and just focusing in a specific area, we can see that is completely linear, the decay. So in our case, we can confirm that it was quite well mixed, the suspension. So here I plot a matrix with some of the results, or better to say, the results for one of the setups with all the mass concentrations analyzed in the x-axis and the main particle sizes in the y-axis, and every plot is the response, the turbidity ratio profile, and the three colors are the three frequencies. And you can see how as we are increasing the concentration and also the mean particle size, the analyzed range is getting more steeper and also higher. And okay, what we did next was getting these features, the slope and both the intercept, and analyze it separately. So I just put here the equation as a reminder. If we focus in the first setup, that was the mixing tank tests, and I plot only one frequency, the 9 megahertz, we see that it follows the theory. For our slope feature that is related to the concentrations, we are getting an increase of this feature as we are increasing the concentration of particles, and also increase of the response connected with the mean grain size value. So the higher is this particle size, the higher is the response and the slope of this turbidity ratio profile. And the same for the intercept, we obtain the same relationship, as it is also connected with the concentration of particles. When we are moving to the fluent tests, so the test in the closed loop setup, we also observe to the same parameters that as we increase the concentration, we are increasing the response of the sensors. But however, in this case, we observe as we increase the particle size, the response is lower. So we were like, wow, the theory in this scenario is okay, but when we move to the fluent configuration, it's totally different. So in this test, we could conclude that this correlation, there is a correlation between the TSS, right, and the acoustic profile, but we are getting different results depending on test configuration. And a possible reason that was also highlighted in the first part of the webinar would be the air bubbles. And here I show some videos of the test. So this is the test in the tank, just in the tank, and this is how it looks like. Also the same tank and the flume during the second configuration. And you may see here, of course, there is a entrainment of air bubbles in the system. So this could be the reason of the difference. So here I plot the same features for the two configurations, and it should follow like in a global calibration, in a global scenario, the same trend. But we look, we can see that there are some differences, and in some cases are accentuated. Also, Stefan mentioned this increase in some frequencies could be possible for certain particles. And we observe also that the effect is almost attenuated for the largest particles. So for the particles close to these 63 references, yeah, we almost get this one-to-one. So this affection was more evident in the lowest particle sizes. And the second experimental campaign was performed in this flume test facility in A Coruña, in the wastewater treatment plant of A Coruña. That, well, now is a coincidence that inside this facility is inside the CoUDlabs project. So you can apply this transnational access that Jörg mentioned in the introduction. So it's available for researchers. But in this case, we use this flume to measure the inflow. So the inflow was mainly taken from wastewater from the inlet of the wastewater treatment plant, and we have this inlet tank in which we measure the characteristics of the particles. And within all the sensors, we install the acoustic profilers. So as a good engineers, we use tape to attach the transducers to optical turbidity meter. So in this case, we use 3 and 6 megahertz transducers, an optical turbidity sensor, and also an auto sampler for getting samples in this case, every 2 hours. And the experimental conditions was with raw wastewater from the inlet of the wastewater treatment plant. And here I'm going to plot a couple of time series. So in the first one, we can see how the acoustic results fit quite well to the samples. But if we pay into attention the optical proof, it seems slightly different, mainly in these parts of the day. But yeah, it was quite uncertain because yeah, if we take into account the second case, it was just the opposite. Like we found a good relationship with the optical proof, but a really bad correlation with the acoustic proof. But considering also the possibility that this technique offers to get information about the grain sizes, we also compute the same features that I presented before to get a correlation with the mean grain size. And for these two time series, we also, with the samples, we analyzed with a coulter the grain size distribution, and we calculate the mean grain size, and we compared it with the signal, and we found a good correlation in both time series. Like there was a good correlation between these features of the acoustic turbidity profile and also the mean grain sizes. And just to finish this presentation, a brief summary, we found that in this campaign, in these two campaigns, that there is a potential application of the acoustic sensors for monitoring concentration and also the particle sizes in wastewater. And the acoustic turbidity measurements were correlated to the total suspended solids and to the mean grain size values, but if we are considering the cases studies separately. Therefore, local calibrations might be required, as we saw. The air bubbles play a main role and it appears in two-red flows, and this distort the acoustic profiles. And yeah, I just put here an open question, maybe for the discussion, like, is it possible to remove this effect from the profiles? Is something that I asked before in the first part of the webinar. And we also see that under combined seaward conditions, we found weak relationships between the acoustic turbidity and the TSS occasionally. But however, a consistent good fit was obtained between the slope feature of the profiles and the mean grain size of the particles. That's it from my side. Thank you for your attention, and special acknowledgements to my supervisors at that time, Jose Anta and Frank Blumenthal.
Okay, thank you for your introduction. I hope you can see my presentation now.
Yes, it's very good.
Okay, today I'm going to share my experiences with acoustic monitoring in a storm sewer, which I made during a pilot project with the goal to plan a stormwater treatment concept for a big separately drained catchment based on pollution measurements. The catchment is located in Emstetten in Germany and has a size of 236 hectares. It contains residential areas in the north, industrial areas in the south, and a main road which leads from north to south through the catchment. And the runoff from these different kinds of areas with different levels of pollution mixes up in the sewer at an early point and is discharged into the River Ems at this point here. And that is close to where the measurements took place. I'm going to show the setup of the measurement site and more photos later on. But first, I would like to give some information about the goal and the structure of the pilot project. The short name for this pilot project is called EM1 due to the description of the discharge point of the catchment in the city of Emstetten, where the measurement took place. And as I said, the goal of this pilot project was to plan a stormwater treatment concept for a separately drained catchment on the basis of TSS monitoring. Therefore, we were doing a measurement campaign with multiple sensors over a period of several months. And the collected data was analyzed and then used for simulations of a treatment concept that was adjusted to the pollution characteristics of this specific catchment. For the monitoring of TSS, we were using an optical sensor, the spectrolyzer from ESCAN in the first place, but we had the chance to use the acoustic sensor Pecher from NIVUS as well. And that's why we could, as a side effect, make some experiences with this acoustic sensor by using both probes in parallel. And this is what the measurement site looked like. The photo on the left side shows the measurement site in flow direction, and the sketch on the right side shows the arrangement of the probes. The first thing here is a where to create a minimum level of 0.2 meters to assure the required minimum level for every sensor. Next, there is the optical sensor, and close to this is the end of the suction line for samples. And after that, we left a bit of space and installed the acoustic sensor in flow direction. And on the back of this one, we installed a flow meter. Before we are going to look at the data, I want to show this illustration of the extent of each measurement area. And I want you to keep that in mind when comparing the optical and acoustic measurement and the laboratory analysis. The optical measurement takes place in a 5 millimeter measurement slot. And the samples are taken from the end of a 10 millimeter suction line, which is close to the optical measurement. And the acoustic measurement takes place in a cone-shaped measurement area here. For the maintenance, we drove to the measuring site every 2 weeks. And the 2 weeks rhythm was especially important for the cleaning of the optical probe to make sure that the measurement slot was not blocked by anything. As you can see, there accumulates sediment and paper or something. And on the contrary, the acoustic sensor didn't get blocked so easily and needed less maintenance. So this is an overview of the data we collected over a period of 6 months with these multiple sensors. Additionally to the sensors in the sewer, we installed a rain gauge in the catchment. So we have information about the precipitation shown here. Next, we have level and flow measurement. And down here, the hydrographs of both the acoustic and optical monitoring of TSS. The red hydrographs show the optical measurement and the blue hydrographs the acoustic one. This color code will be the same when I show some events on the next few slides. Aside from that, there are some black and gray dots that show the concentration of TSS and TSS 63 from the laboratory analysis. And if we go closer into the data and look at single events, in this case, an event where we also took samples, we often see a picture like this. When the flow begins to rise, the TSS concentration increases rapidly, and later we see a slow decrease in concentration. This characteristic has been monitored with both sensors as well as in the laboratory analysis. But if we look at the absolute concentrations, we can see differences between the different types of measurements, especially in these first peaks. The acoustic measurement shows higher concentrations compared to the optical measurement. And in this case, the acoustic measurement is closer to the laboratory analysis. Later, they are both quite close to the laboratory analyzed concentrations. This is another event which shows a similar characteristic, the rapid increase and slow decrease in concentration. Overall, the concentrations in this event are quite low and a little bit underestimated compared to the laboratory analysis. And this time, the optical measurement is closer to the laboratory analysis than the acoustic measurement. As the acoustic sensor offers the possibility to have a look at the particle size as well, I'm displaying the TSS63 hydrograph and the TSS63 concentration from the laboratory analysis. And here we have we see big variations. The laboratory TSS63 is more or less in the concentration range of the entire TSS concentration of the optical and acoustic measurement, but definitely higher than the TSS fraction of the acoustic measurement. This last example of monitored events shows some bigger differences among both measurements, as well as compared to the laboratory analysis. But here I have to say that this is not a plateau. In this case, we took a composite sample. So this is the medium concentration over about half an hour. For this event, we also have the TSS63 fraction, which is similar to the laboratory analysis of TSS63. And one can say that the optical measurement is also closer to the concentration of TSS63 than to the total concentration of TSS. So let's see what we have learned about monitoring with an acoustic and an optical sensor in this storm sewer. Most of the time, both concentration hydrographs show the same characteristic, but there can be differences in absolute concentrations, which can sometimes be quite high. Considering all samples, the optical measurement is closer to the laboratory analysis than the acoustic measurement, but I'm not sure if that means that these concentrations are more realistic or if this may be due to the positions of the measurement areas and the sampling point. Moreover, we have seen less disturbance with the acoustic measurement and less maintenance was needed for this sensor. But on the other hand, the acoustic sensor requires a minimum level of 0.2 meter, and therefore we needed a wear. On the last few slides, I want to come back to the mission of the pilot project to show how we used all of the collected data. We analyzed the data, and the most important findings are that the pollution of the stormwater from the catchment has a high but characteristic dynamic, meaning the rapid increase at the beginning of events and the slow decrease. But overall, the pollution is quite low, with a lot of events with TSS concentrations under 100 milligram per liter. In the next step, we were building a model of the catchment using the software SWIM, fed the model with our precipitation data, and calibrated the flow and the pollution buildup and wash off using the data from the measurement campaign. And this is how the simulated hydrographs looked like compared to the monitoring data. The green hydrographs are the ones from the simulations, and the blue, respectively, the red hydrographs show the measured flow and concentration for the same event. As a last step, we used the calibrated model to make simulations of a treatment concept where the flow gets separated based on the pollution, and only the high polluted parts of the flow will be treated, whilst the low polluted flow goes directly to the discharge point. And for this catchment, the simulations showed us that a threshold of 45 milligram per liter is suitable as a control parameter for the flow separation. And using this control parameter in a simulation over a period of several years has shown that on average only 14% of the flow have to be treated with a high efficiency to achieve the required efficiency for the whole discharge, when only the most polluted parts receive a treatment. So as a conclusion, we can state that the pilot project has shown that it is both ecologically and economically advantageous to measure the actual conditions on site and to adapt the planning of a stormwater treatment to these conditions. In the observed catchment, both monitoring techniques, the optical and the acoustic one, are qualified to deliver information about the concentration characteristics during discharge events, but the comparison of acoustic and optical TSS monitoring to the laboratory analysis has shown that there are still uncertainties with regard to the absolute concentrations. Therefore, a few samples should be analyzed in a laboratory to verify the real-time data. So this was a short insight into a practical application of TSS monitoring in a storm sewer. And lastly, I want to thank our sponsors and partners who helped realizing this project. And I want to thank you for your attention.
Just a second. Okay.
Yes, and
so,
before we go to the topic,
yeah.
can you maybe say 2-3 sentences about like your experience, like
Yeah.
who you are and what's your
Okay,
experience?
I'm a researcher from Strasbourg, from EAWAG laboratory, and my team are working on acoustics in wastewater for, I would say, quite 20 years. And as Daniela showed before, we mainly compared measurements to optical data, which is also given, which is used to drive the treatment in wastewater networks. So we saw a lot of differences, and we wanted to know why, and we'll tell you a bit more later, but that's the reason why now we are working on a new technique, which is time-resolved optical turbidity, as I show you on the first slide here, that we named TROT for the initials of this technique. So it's really new. It means that we are still working on it. It's at the time really promising new real-time technique, which is still under development. I would say we are at TRL between 4 and 5. We have 2 prototypes working, and we are still working on it, so we are still making progress on the data. What I have to add is that this technique is made possible with the progress in electronics, which is going cheaper, and which allows us to use a medical technology on the field, which was not possible before. So what do we do? How does it look like? We'll show you this. So that's the concept. Knowing that we are in the final having an optical probe that we are putting in the medium to make the measurements. This optical probe, consisting at the moment of 2 optical fibers, is linked to electronics, which is a homemade ultra-fast electronics device. And the goal of this technology is to get in real time turbidity and velocity measurements. And how do we think that we get these measurements? It's explained on these 2 diagrams. Here is a trot principle. So first we have an emission fiber in which we will get very short light pulse, so 100 picoseconds that we led to the medium. And we have a reception fiber, the other one, which will allows us to get the information we want to know. So depending on the way the light moves between these 2 fibers, we will have different information. And we are looking at the light photon by photon. That means that, for example, if you look at the red path is rather short, and this means that this photon will be arriving earlier than the photon that will follow the path here in green. So what we are doing is that we are using multiple pulses to get the measurement for each photon. So we are building what it is called a time point spread function, and which is a histogram of the number of photons as a function of its arrival time. That means, for example, here on the other diagram, for pulse 1, you have a photon that will arrive quite soon after its emission, that you which is shown here. For pulse 2, it will be a bit later, and so on. And we are counting the photon as versus their arrival time. So this is the time-correlated single photon counting, which we are using for this technique. So here you have some results. Here is a typical time point spread function. Here are measurements that were made on water and sand suspension at different concentration and different sizes. And here you have one of the main parameter of the time point spread function, which is the number of photons. So here you have the evolution of the number of photons as a function here of the various concentration. What I have not said yet is that we have not only the number of photons, but we have also here an exponential tail of the spectrum and also other information like the mean time of flight of our photons. And combining all this information gives us more information as just optical turbidity. So we made the measurement that I show here at the DEXMES experiment, which allows comparison to other techniques. And here are some brief comparisons. Here you have what we see on optical turbidity and also on acoustic backscattering for given types of particle. So we were looking at how well we can follow the concentration of a known type of particle at a given concentration. So that are lab experiments. So we know very well the concentration and the type of particle that we are using. And we used kaolin, which is very small mineral particle, about 5 micrometer in diameters, We also used wet stark particles, approximately 20 micrometers in diameter, and also Kieselguhr, which is also a reference. This is used in optical turbidity, which is a rather mineral particle, also with a diameter of quite 20 micrometers. What is interesting to say about these particles is that kaolin and Kieselguhr are mineral particles, very hard, that will very well reflect acoustics. And in the contrary, wet stark will be soft particles that will not have the same behavior to acoustics that hard particles, mineral particles. And that explains a part of the difference I will talk about. So here in the first graph, you have the optical turbidity as a function of the particle concentration, measured here with a Solitax turbidity meter. And you can see, which is expected at the beginning, you have a nice proxy of suspended particles. You have a linear relationship between the concentration and the optical turbidity. But if you increase very, very highly your concentration, you have here a plateau, which shows a dysfunction of the turbidity meter. And worse, after you are still increasing your concentration, you can see that your optical turbidity meter works again and will show you here a decreasing turbidity with increasing concentration. So for a given turbidity value, you can have two concentration, a low one and a high concentration, which have to be disambiguated to have a reliable result. So here I still talk about the colors. In blue, you have the kaolin, which is very small, so very sensitive for optical particle. The wet stark in here in red, and Kieselguhr we don't get high enough in concentration. We were out of Kieselguhr, but you have quite the same behavior for Kieselguhr as for wet stark for optical turbidity. Now coming to acoustics, we looked at acoustic backscattering in the same way that Manu told us about before. We were looking at the slope and the intercept of the acoustic signal, of the logarithm of the acoustic signal. And we were plotting here the dependencies of here logarithm of concentration and value of the intercept. And here again, particle slope of the acoustic signal as a function of the particle concentration. In both cases, you can see that you have nice linear behaviors for bigger particles like wet stark or Kieselguhr, and you have really, especially for, I would say here, the first term, which is the intercept, which is more representative of backscattering, you have unsteady measurements because you are very close to the signal to noise level for having a good acoustic signal. And here you have the same for the attenuation side, so the slope side, which shows you that for the different particles you have something that is better, but still very unsteady for the kaolin. And I didn't mention before that we used UBLab devices for these acoustic measurements. So we made the same measurements on the same type of particles with our new technique, so TROT. And here we looked only at the normalized number of photons. And we can see here that we have also this ambiguous behavior for kaolin. That means that you can have the same value for two different concentrations. You have linear dependency for Kieselguhr, and also a nice linear dependency for Westark. On the contrary to pure optical devices, here for the normalized number of photons, if you look only at this, you cannot know on which side of the curve you are. But if you are using other information like the time of flight of the photons in the medium, you can have another information, and you can see here that we have a decrease of the mean time of flight, and followed here by a slow increase, which allows us to separate on which part of the curve we are compared to only the use of the normalized number of photons. So if you want more details, you can go and have a look at our publication. The main lesson about ROT is that this technique is quite equally sensitive to small and large particles, that the measurements dynamics on the particle we tested is increased by quite a factor 3. And I will show you some preliminary results. The techniques seem also insensitive to biofouling, which is a major problem for optical devices, especially in wastewater. So here we have made some experiences with filters. Here you have the optical density of the filters, which means that attenuation is 10 up to the number you have here, so 10 up here until 4, attenuation of the light beam going through the filter. So as expected, we have a decrease in photon rate that's shown here, which is a major problem of classical optical devices. But, and this is the nice part, if we are looking at the mean time of flight, and so here you have the mean time of flight as a function of the optical density and also as a function of various Cowling concentration. We have for the same concentration always the same time of flight, which allows us to know exactly at which concentration we are. So this is laboratory results. We don't know if we are well reproducing the real biofouling, and we are working with colleagues to test it on real biofouling in marine exposure this summer. So we will know more about it after this summer, but it seems very promising. And to finish, to summarize somehow all what that was said today, I would say with experience that optical turbidity is very effective on small particles like sludge or fine particles in rivers. That acoustic turbidity will be more efficient on larger particles like sand. And in my mind, that two techniques are really complementary. And at the lab, we are working, it's a project, but for us, the future of sediment transport monitoring lies really in a combination of optical and acoustic signals at different frequency in order to have an information about the particle size evolution that you don't have yet with a single technique. So I thank you for your attention. If you have any question, don't hesitate. And I think that you will all agree that after that, all we have heard today, I think it's really important to combine the two techniques, also using optical turbidity and acoustic backscattering to have a better knowledge of what is happening in wastewater and sewers. Thank you for your attention.